Okay, go to the cloud. And then how was it that we can do customized? I wanted the GPU actually. There you go. So change runtime type. I'm going to do the GPU. Okay, so it's GPU anyway. All right, good. So
do you see much of a difference between different runtimes?
Not really at this code, but what I wanted, the GPU is also, you have to specifically declare that you want, because the GPU units, they also have a CPU, right? It's just like the hardware, wherever that thing is running on Google, it also has GPU cards on it. So, but you need the CPU to run like the basic the computer. But you need to declare the GPU usage, which I don't have in my code. The reason I'm using it is for a different, So where was it to be? I mean, there's many tutorials like how to do that, but you have to. Let's see if I can find it really quickly here. Memory limit, I guess, is more complicated than the one. But if you go how to use TensorFlow GPU, maybe this. With device or something similar. So you have to declare it that your code then is going to run the GPU, which you're not doing here. So it's essentially it runs on the CPU. But the reason I'm doing it, I'm hoping to run this TensorFlow dev, if we make it there at the end of the lecture today, which is kind of a website set up by Google where you can publish. Of course, you wouldn't publish any private data or whatever, but you publish the results of training your model for everybody to see, free host and free public website by Google. And it seems this one, I actually just started using it for the lecture today. It needs GPU to work, so I don't know why. So that's why I want to have the runtime set up from the beginning. Okay. And then, yeah, so that's why, if we get there. And okay, so I'm going to go ahead and get started with this. And let's re-review. Of course, we need to install the Spectral. Let's re-review really quickly what we had the last time. And for everyone, if you have your microphone on, please mute it. So make sure there's no background noise for the recording. Okay, so we installed the Spectral, and then this we explained here last time, but really quickly. The NumPy we import, TensorFlow import, the callbacks. Can somebody let's do it more interactive? Can somebody tell me for those three, and then somebody else who can do the rest? What is this used for? This one, and this one. So what is each one of those things? Who wants to volunteer an answer? And then the name is kind of self-explanatory, right? So you could just, I mean, I'm hoping that everybody studied the material from last week. It was a lecture. Tong, go ahead. I saw you raise your hand. Tong, you want to answer a question? I think we can hear you, even though now it's breaking up. So I'm not sure if it's a problem with your microphone. Anybody else wants to volunteer? Like this stuff, you know, I'll explain now really quickly, but it's on detail, and it seems like, I mean, nobody's studied or nobody's in the mood to answer. This is like, if you want to say you, okay, you can see the screen. Is there any issue? Like, is the share screen not coming through for everyone? I'm just making sure.
I can see it.
Okay, so maybe it's localized. Anyway, I'm gonna go ahead and explain it for the interest of time. And thanks, Tong, for volunteering to answer the question. But again, okay, Afsana, you want to go ahead and answer?
Sure. I don't know the details. I just know the general ideas.
No, that's fine.
Yeah. Like the early stopping is basically making sure that once you're training the model, essentially you don't overfit it essentially. So making sure that you stop it at a certain point. I think the categorical cross entropy has something to do with the loss function. And then the import atom essentially make sure that you optimize the function. I'm not exactly sure about that one, but it's something to do with optimization.
Yeah. So so that's right on. And as I said, also it's self-explanatory too. I mean, some concepts for example, optimization, it's essentially as it says here, as optimizers. Remember we mentioned the back propagation. So there's always three things you need to remember, or I guess two things, or we can say three. I guess three should be better. Three things that are in the neural training, artificial neural networks, right? So what you're training, as we mentioned many times before, is essentially the weights, right? That's the only thing that's modifiable, the structure connections between the neurons. The structures of the neural network is fixed. What changes is the weights, which is the strength of the connections between the neurons, like in the brain, the learning processes strengthen the connections between the neurons. So that's what you're training, the weights. So that's number one. Number two is as you do the forward pass, one forward pass with the data, you get predicted values, and then you compare to the actual values that you have in the training data, and that difference is the loss. So that's number two. You calculate losses, and based on the losses, which is the difference between the predicted value and the actual value, you adjust the weights. And now you want to, so that's number two, is the loss. And number three is to know how much to adjust the weights based on the loss, right? So, if the loss, say, is going negative, you adjust the weights positive, or the other way around. And if the loss is big, you do a big adjustment in the weights as the loss is being reduced with the epochs, the cycles that we're doing with the training. You do smaller and smaller adjustments. And the way the adjustment works, that's number three, is the back propagation, which is what we call, I think I posted the link on the Blackboard too, some very crazy calculus, which is the gradient descent. And essentially, this gradient descent is calculated is an optimization problem to find the best local minimum, minimize the loss. And that's solved by an optimizer algorithm, and that's what that is. So we have, number one, weight adjustment, number two, losses, and number three, gradient descent, which is calculated by optimization algorithm. So that's the three stuff. And then the early stopping, as you correctly mentioned, is not too overtrained, meaning if you train too much, it gets sort of fixed, a brain gets fixed in its own ideas and doesn't want to learn new things or hear new opinions or whatever. That's the overfitting. So that's what the early stopping does, but also it has a dual role because our models, they run pretty fast because they're very simplistic, but when you have huge data sets, you don't want to run those extra epochs, because each cycle is the whole set of calculations, along the network, summations, logit function, and then the loss function in the end, and then the back propagation, and this takes time computationally. So once you reach an acceptable, that's what the early stopping monitors, the when the losses gets minimized, why keep running the model and risk overfitting, and also mostly also important to waste this computational time and energy to do it if it's not improving further, right? And what I also not utilizing the GPU. Interesting. The Google complaints, or we'll leave it. They have plenty of GPUs. So also, again, I described, and you guys need to go if you want to also really say that you took a machine learning course for bioinformatics and really understood the machine learning concepts. And that's why I keep repeating the lectures, but you guys have to go watch those lecture videos carefully. You have to, you know, really replay the video where I explain the concepts and stuff. And also, you know, if you're not into like really looping the stuff, you can also try to read up the concepts from the web or other materials, the books we posted. So it's key that you understand the concepts, right? And I would like to ask what an epoch is, but let me explain it for the interest of time. So an epoch is essentially what we described, right? Forward pass, doing all the calculations with the weights, calculating loss, based on the loss, doing the gradient descent and back propagation, how we call it, and then adjusting the weights. So that completes one epoch. And then you do the same thing, forward calculations, calculating the loss difference between the predicted, that your forward calculations output the predicted Y, difference with the actual Y in the training data, and based on the difference doing the gradient descent. So that's a second epoch, right? So those are the cycles we're talking about. So that's another definition. Okay, so those are the stuff here. And then the spectral is essentially something, as we mentioned, it's like we were using the network X, right? In the beginning of the semester, which is for graph data. So essentially, this is for graph data too, but it's a data structure for machine learning. It's not a data structure library. We want to be precise in our concepts. It's a library doing machine learning with graphs, so it has very useful functionality to be an intermediate between the graph data and the TensorFlow, which is like tensors, multidimensional matrices. So essentially, it helps transition the data from the graph data structure to the tensor data structure. So you can work with graph data with TensorFlow, right? So that's what the spectral is. And you know, we posted the website. I don't expect you to read everything, but read the sections that we discuss. We'll ask that in the final two. The sections we discussed in the class, and we have posted on the Blackboard or using the code to understand the concepts, right? So single loader is for essentially when working with a single graph. So remember, we said the training is we can have a single graph with known nodes and unknown nodes, and then the whole training process with the information or signal propagation along the graph that we've seen, you know, when we're doing those matrix multiplications and all that stuff. This signal propagation helps annotate the unknown nodes, right? And because we have a single graph, there's a single loader, but it can be also training where you have multiple graphs, and essentially you, instead of putting labels on a single node, you put in labels on the whole unknown graphs, right? And this is a whole different domain and how to think the algorithms there. So we don't go into that during this course. And the models. So this is an artificial neural network model, kind of like we were saying, the convolutional neural network, right? So I can pull really quickly. I'm sure most of you remember. So remember those pictures you were seeing where we had the convolutional layer, the pooling layer, and usually those go in pairs, convolutional and pooling. And then we have the flat. So the model is the different layers we add, right? So with the spectral here, it has that model, which is all together. And we'll see later today how we can also break it down and not break it down, actually recreate this model from element by element, essentially. And that's another of the powers of Spectral, which because it's all TensorFlow underneath, you can use the models that Spectral has. And if you're curious, right, maybe you've done that already. I hope you did. Let's see, do I have this model here? Yeah, so that's the GCN model. I mean, here in the ports it's a little different, but it's exactly the same thing. And that one, does it show the formula here? Well, if you see the paper, you realize, actually, I can put it on the layer. So you can use a whole model which has everything, essentially. I mean, it's not, this is for images here, working on graphs, but it's the same idea that it has all the layers that you need, pre-assemble it, but you just need to import one and it works. But in Spectral, you could also do it layer by layer, which we'll do one part of the code later today. And I'm just going to show you the core layer, meaning that this whole GCN model, it's composed by many of those GCN convolutional layers, like we see here, which are getting stuck together, but you get it as one package and you import it. But if you were to do it like layer by layer, which again we'll do in a further cell down the code, you just import this layer here. And as you see, so this GCN model, graph convolutional neural network, which is convolutional neural network, like we've seen before, but on graphs, it has its core, this graph convolutional neural network convolution. That's why it says GCN graph convolution neural convolution. I guess that's how he named it. And that layer, it shows you the formula here, which is the matrix multiplication, which we've seen before. And this is the standard in the field by the Kipf and Wellen paper, which is this matrix multiplications, which, as we've seen, they work very nicely to propagate the information along the graph, right? So that's so you know what's going underneath the surface there. And then a couple more things that we have: the pre-processing. So you can see here convolutional layers. You can see base layers. So this would be is the pre-processing here. It's a little messy, the documentation. I mean, it's an awesome library, but it's a little messy. So where's the pre-processing? Pre-processing should be creating data set, getting started. And I say it's messy because this is a pre-processing layer. Should be under the layers. Convolutional layers. Now this is all the convolutional. Maybe it has it in the data modes. Data set example. Anyway, I'm not going to spend time now to find it, but the documentation for that pre-processing layer is somewhere in there. The Spectral, I think maybe he has it under the data, but if you wish to write the documentation more proper, I'm not complaining, still it's an awesome library, he would put under the layers, but it's somewhere in there. So that's being used to pre-process data, right? So this is data pre-processing. That's the underlying convolution layer, which is many of those are stacked already within that model, which it gives you ready to use. And he imports that layer here as well. And then the data sets. So we work with the GraphSage, which is a single data set. And then this is the TU. And remember, we saw all the websites. I mentioned the Open Graph benchmarks, the OGN, the TU website, review all the lectures. The sooner you start reviewing it, the better it is, because this one has multiple graphs. We're not going to see it today, but if not for next week's homework, for the final, it's going to tell you, like, go on one of those websites that we've seen, and just tell you the name of the website, and we have the template here, how you import data sets, and tell you go to import that data set in your code, right? Of course, since I said we're not working here with data sets which have multiple graphs, because we only within the model with information propagation and a single graph. I'm not going to expect you to do training of multiple graph data sets, but since we've seen the last time and I'm reviewing now how we explore a data set, I would expect you to, as part of the what's being asked in the homework or final, to do those operations and answer questions about the data set. Okay, so here I'm just downloading the graph sage, which has a single graph inside, the 2U data set, which has multiple graphs. We'll leave it for now. You will explore it either in the homework or final. And you see, so this one is basically, like you assign any variable. That's what you do here. It's just that the variable is a graph sage object, which, if you're wondering what those objects are, and when you say object, I mean everything in Python is an object, right? Even when you do something like that, you say my array, you just create an array object, right? Because Python is 100% object-oriented language. So this one, where does this object come from? From Spectral, right? If you go data sets, right? So where's the graph sage? Yeah, there it is. So you just import it, and then the documentation is kind of sparse if you want to use the pre-processing or not. I think even without this one, it wouldn't make much difference, right? So this is built into Spectral, and this is what we imported here, right? So this is the object, or in the module of the datasets.graphsage, which we imported, and then we use it here. Okay, so now we have the whole graph as the graph sage object, which is the object in Spectral, which is designed to bring this data in, and we're going to go explore it. But again, we covered that stuff in the next lecture, so that's why I'm going quickly through them. Any questions to what I mentioned so far before I go on? Okay, so there's no questions, and I'm hoping you all understand those things, because it's very, very basic, right? Okay, so question of Sana.
Can you quickly re-explain what the random seed that line does?
Is it actually, we actually use this? Let me see. So it's defined here. It's defined here. I mean, the random seed, obviously, let's create a random number, and I don't know if you've done it in your earlier courses. Any language, Perl, Python, when you use the functions that create random numbers, you have to give a seed, which is like you can think of it like rolling a dice, right? So you give it a random number to start with when it rolls the dice, kind of thing, and then produce random numbers based on that. But my question is, like, I think because this code, I got it from the Spectral, and I've seen this seed before. So that's the definition of the seed that I said before. But actually, I don't think it's being used anywhere here in the code, because it just, the weights, you see, we'll explain further down, it's just initializes the weights, not in a random way, because you can control in TensorFlow how you initialize the weights, so you can make them completely random using the internal randomizer that TensorFlow has. And that's in the documentation when you specify, actually, if you don't specify anything, the TensorFlow, when it starts the training model, it uses its own random weight initialization. I guess this person was planning to define their own weight, random weight initializations to override the default that TensorFlow has built in. And I put it here in the code and was never used because I don't see it. I mean, I see the seed being defined as a variable, start from 0, so anything from 0 and above, and then doing the calling the randomization function here, but actually doesn't use it anywhere in the code. It just uses a different way to initialize the weights. And I think, as you'll see later on, that's the reason why the training, because of the weight that he sets. We're not going to have time to explore that. I'm not going to ask you to do it as part of the homework, but for those of you who are more inclined in the software developer and you want to explore that, I'm putting it there so you can go ahead and try it. But as you'll see, I think, so he's not using the TensorFlow built-in, which if you don't do anything, the TensorFlow is going to build in randomize the initial weights. He's trying to define a randomization that he puts in the code, but he never uses it. And then you'll see he's using like a scheme to create the weights, which I think it creates very bad weights. That's why, as you'll see when we run it, the model, it has like a lot of it's not a good, the training doesn't work well. So but again, this is a code that they wrote as example, and of course we're great that they put it there along with the spectral library, and we can use it instead of having to write stuff from scratch. So short answer to your question is this is the randomization. I mean, any programming language, you can look up randomization, how you do it with a seed. So he tried to create a randomizer, but he doesn't use it anywhere in the code. And yeah, so we downloaded the data set already. And then here, remember from the last time, we did explore the data set, which you'll have to do it in the subsequent assignments. So the first and the best way to explore data sets is to print out stuff. And this one, if you want a reference, right, I put it here, the link, getting started. So all this stuff that we explained, probably now it's the 5th time, what is the stuff in the spectral. Again, I'm reviewing now, so I'm not going to go into details. Of course, feel free to ask any questions you might have. These questions also, like when I said you have questions from the last time, which is where we cover that stuff. Of course, you can ask now. But let me go ahead. Please interrupt if you need questions, no problem. I'll keep going for the interest of time to explain what it's in here. Which again, we covered the last time. So how many graphs do we have in the data set? Right, print the length of the graphs. We need to go up a little here. Just one graph, right, as we mentioned. And then how many, let's get the first graph, right? So it's basically the graphs in the dataset object, which we loaded from the graph stage, is an array of elements. Each element represented a graph object. So it's a graph stage object containing this the graph stage data, and it has an array of objects, each object being a graph. This array has a single element, 0, because it's only one graph, and that's what we get in here. If you put 1 here, it's going to say array out of index because it only has one element, the element 0. Right, so we get that first element and that single graph that we have, and then we go ahead and explore it. So I'm just printing how many nodes we have, and then again you go to the spectral documentation to refer to that stuff, right? So the node features is essentially the node annotations with the .x. which is, the one hot encoded stuff, which we put on top of the nodes. And then let's see. So how many nodes we have? So we have a single graph with 56,944 nodes. And then how many node features we have? That's what I'm printing here. All right. So so the node features also is an array, and each element is the features for one node, right? And because we have 56,944 nodes, the array of the node features, one for each node, is also going to be 56,944, right? So if you print the length of the graph.x, which referring to the spectral documentation, you'll see is the array of the node features. Because we have 56,944 nodes, that's how many entries we're going to have in this array. So if you print that one, right, you see it right here, has many nodes. And let's print the first element for the first node, right? So I'm getting the graph.x, which is the array with the node features. I'm just getting the first element of that array, which is the features for the first node, right? And you see here, it just prints that stuff, which is the one hot encoded for that node. Not very good choice because everything is zeros. I mean, it doesn't really matter because 1 and 0, they both have equal meaning, right? So we could try another node, right? And it doesn't matter because all nodes have the same number of features here. And this one I'm printing the length to see how many go up again. I'm printing the length to see how long is it. I guess the fourth node with index 3 is the fourth node. It also has all zeros, but you can try another one. You'll see like some of them, they have ones and zeros. It's here in here like we were doing with the one hot encode. And then I print the length of that, so it's 50. So you can count it if you want. So each node has 50 categories there for the one hot encoded, like we explained like way back in the beginning of the class. Now node labels. So here is a little more complicated. I mean, same idea, right? The node labels is the .y, right? And we print the first the labels. Well, how many node labels we're going to have? Also 56,944 because each node gets a label. And then we print the labels for the first node. You can try printing any other node you want. We can print node 56,000, and let's see what we get. Here we go up a little. Let's see. Yes, the node labels. Yeah, so see this one, the node 56,000. It was a little more interesting here. So how many node labels have? 56,944 because each node gets its label, and that's how many nodes we have. Now this is and I'll explain that this is a label for a single node. Why it looks like that? Because you would imagine the label being just 1 or 0 or some other description. I mean, every description, it would have to be one hot encoded if it's a sort of a word description, right? For the labels, it would have to be one hot encoded to be able to be used. But if you go the graph sage from the links in Spectral, which is the website in Stanford, right? Well, I'm not going to do it now. You'll see that essentially what they did to create that huge graph with 56, almost 57,000 nodes was that they aggregated data sets from different databases, and whenever they have an overlap, they just basically merge them in that big data set. And because there are so many different databases, those databases is epigenetic data, mutation data, and so on and so forth. So they ended up with a huge set because they merged the different things, and they got a set of possible labels that you have in a node, and the labels being like, is it a cancer mutation? Is it methylated? is it does it have this epigenetic mutation, right? All these biological characterizations of genes or proteins or something, right? And that's why the label ends up being actually more bigger than the node feature, but it doesn't really matter. It's just basically the categories, right? That's what the one hot encoding is. So you know, this node, for example, whatever these categories might be, we don't care. It would be like, yes, it's methylated. Yeah, it has a cancer mutation. Yes, it's hydrophilic. It's not hydrophobic. That's why it's 0. And you know, it's not something else, and so on and so forth, right? And again, they ended up with so many potential labels because they brought all those different data sets together. But if you had, say, one data set, right, a single database, which was just cancer mutations or non-cancer mutations, you might have just a single label, 1 and 0, 1 is mutated, 0 is not mutated, right? But it doesn't, whether you have 1 or have 121, it doesn't really matters. It's just labels, right? This one has this set of labels, and other nodes will have a different set of labels, right? And just try it, put different node numbers in, and see how you get different labels. And the same for the node features as well, right? Put different node numbers in and see if you get like different node features. And I'm just paying attention to that stuff and ask questions you might have, because that's what we're going to be examining in subsequent homeworks and the final. And then the length of that is, sorry, I lost it. The length of that is 121. So edge features, we don't have. This is, I mean, it's not uncommon, but it's not so common to be used in graph neural networks. And here, the edge feature, which is represented with AE, we don't have it. And you see here when I print it, a number of labels. This one, you know, we saw it before, 121. Essentially, what we counted the size of the labels, and we printed here, is also build this the variable data set number of labels, right? So that's what's here. And then finally, the adjacency matrix, which is, remember, the coordinate format. So you see one adjacency matrix here and how you present it with coordinate format. We explained it many times before. You can go ahead and read it, but also I will tell you, as we said, this saves because it's a 56,000, almost 57,000 node graph. So you would represent that 57,000 by 57,000 matrix, very big. And this one saves space to basically just enter the connections, right? Because it will be very sparse. Like, for example, the node 0, which only has 4 connections, I guess, with itself, because you see here 0 to 0, so it does a self loop. With node 372, with node 766, and 1101, and that's the weight of the connection. So it's a weighted matrix, but it only has not counted in itself 3 connections. So essentially, it would be all of the 56,944 columns empty except 3, right? So that would create a lot of wasted space, and that's what this CO coordinate format does, where you just specify the node which it connects to and what's the weight of the connection, if there's a weight of the connection. If there's not, it's an unweighted matrix, then all that stuff would be 0, right? Or it might be a fixed weight 1, like we do when we create an adjacency matrix of an unweighted graph. Essentially, the 1 is not a weight. You just say like it's an unweighted graph, so you just put a 1 wherever you have a connection. So you see, you save a lot of space, and there's nothing to worry about this format. I'm just explaining it here for you to understand. All this is handled internally by the spectral, and then if you want further information, that is basically NumPy array or data structure, how they store these things. So the spectral underneath is essentially TensorFlow and NumPy. I mean, TensorFlow, which is tensors, multidimensional matrices, is based on NumPy, right? So TensorFlow imports NumPy, and then Spectral imports TensorFlow, which has already imported NumPy. So it's this whole tower of code there, if you will. Okay, so this is the review of the stuff we did last time, and the weights to review it again. Any questions regarding those things? Again, remember, you have to do those things for a different data set as questions to subsequent homework or final. Okay, so now the weights, we explained it in the last lecture in quite a lot of detail. So I'm not going to do it here, but remember how we mentioned is essentially the weight is like I'm sorry. Before we go to the weights, let's talk about how we train, right? So can somebody tell me what's the different splits we do in the data sets and why? When I say splits, I mean training, validation, and testing. Why is this being done, and where it's being used, and what's the purpose? So could somebody do a take on that? This is also something we explained before. Guy, you want to go ahead?
Sure. So I think you divide up your data into a training set, validation set, and test set. So you first train the data or train your model with a good portion of your data, and then you have some of your data left over to validate. Actually, I'm not really sure what the validation set is for, but then the testing is, just simply to test that you're training your data correctly. So I'm not really sure actually what the difference is between the validation and the testing.
Yeah, so essentially the and like you said, you split it in portions. The biggest portion is the training, and usually the split is like 80% of the data training, 10% validation, and 10% testing. So the validation and the training are used together during the training process. So the reason for using the validation, I mean, obviously, the biggest chunk, the 80% of the training, is you just keep feeding it and doing the forward propagation. And when you finish the whole training set, that's one cycle, one epoch. And then the second epoch, you adjust the weights and feed it again, right? But also, like if you have, you'll see, just I'm mentioning here as a parenthesis, you'll see here, there in the code, something is a parameter that says batch, which, if you have like millions of data, like millions of images or whatever, I mean, here we have 56,944. So you can do those in one pass. And in one pass, the computer needs to save in the memory all the weights. So then it calculates the final output and does the losses and all that stuff, and then the gradient descent. But if you had millions of those, then it would be very difficult to keep huge hardwares to and memory to keep million. I mean, it's actually going to be trillions, because you'll see like every line, every connection in the neuron gets its own weight, right? So if you had even a very simple neural network, and usually the neural networks is much in practice is much more complicated than the ones we've seen here. So it's going to be like a lot of lines, and each line getting its own weight, and then feeding its data point in and having like 1,000 weights for each data point times 1 million images. So if you were to accumulate all those before you do any calculations of losses, it will be very difficult from a technical point of view, unless you have a computer with terabytes and terabytes of RAM. So what you do is you break, that's the term you'll see, batches. You break your data set in batches. So you give it one batch, calculate the loss, the other batch, the other chunk of the training data set, calculate the loss. So it's 80%. So you have your whole data set, you do 80% of it for training, and that 80%, you even break it more in batches and give batch by batch. And at the end of each batch, you calculate the loss. And once you finish all those batches, you finish your whole training 80%, and that's one epoch. And then you go again for the second epoch, batch by batch, right? And again, the only reason for doing batches is to to avoid like basically crashing your computer. So that's 80% the training data. The validation is actually used along with the training data during training of the model, the model.fit, as we'll see below, which prints out the training epochs. And the validation is basically used as a check to see that you're not overfitting the data, overfitting your model. And then after the training is finishing, then you have the last 10% of the data you get, which is the testing data. And then the testing, the way it's being used is essentially you pretend it's unknown data, right? So you have your train model, and then you throw the testing data in your train model and see what predictions it does, right? And that would be the scenario if you had trained a model and you had new unknown data, and you would throw them in and it would make some predictions, right? This is unknown data, so you get the predictions, and that's what the model gives you out, right, when you use it in the real world. But for the testing data, the testing phase, the last phase after our training, because you get the predicted labels, but you know actually the real labels. So then that's where you compare and see how well your model is trained, right? So you would say like you have a well-trained model if on your the last phase, the testing data, which you pretend is unknown, and it gives you some labels, you compare it with the real labels, which you know, and you see like they match to say 98% match, and you say my model is well trained, so I can use it, I can unleash it to the world and use it for real data sets. And just to put this in a context, because here we are absorbed in our bioinformatics in our little world, but what would be a kind of model in the real sense scenario? Think self-driving cars, right? You train an image recognition model to recognize, okay, this is a turn, the car needs to turn, or this is like a tree, the car needs to avoid it, right? So you would really need to test your model with the testing data you throw in, and you see if predicts that is a tree, this is a turn, this is another car and needs to brake, and then you see what the prediction the model is doing, and you compare to the real labels, and it better matches, right? Because if it says the self-driving artificial intelligence model for the Tesla car or whatever, it says it's a right turn, and the actual label says it's a left turn, then you have a problem. Better not release this model in the real world and install it in the self-driving car, whatever, because obviously the results are going to be disastrous. So this is what you have to keep in mind if you're to put in the real world context. But of course, in our case, it can be pure research, whether you get the right predictions in the research model that you use. And of course, it can be as disastrous as in the self-driving car model that you mentioned, because say you train in a neural network model, like we mentioned before, to predict essentially artificial intelligence, right? Substitute the role of pathologist seeing X-ray lung images and predicting if that's lung cancer or COVID infection or whatever. So you would want, if you train a model to do those predictions based on X-ray images, you would want the model to do a good job, right? Because it can be as disastrous wrong predictions as in the self-driving car scenario. Okay, so this is the whole idea. And I see a question from Mariam. Go ahead.
Yeah, I'm not sure if we covered this. I can't remember off the top of my head, but is there like a measure of how accurate your validation or your network is, or is there like a cutoff that says it needs to be this % accurate or needs to have the correct guesses this % of the time? And does that like vary depending on what you're working with?
Yeah, so it's basically the answer would be like, if you say you're 95% correct, of course 99% correct would be even better. So that would be the overall metric, and that's what's captured. I guess we haven't reached there yet, but you guys, you can also look the previous lecture, and we'll get there later today, which is essentially the loss, right? So you want to minimize loss. So that's the evaluation results, and then so this is the loss with the test data and the accuracy, right? So the closest, and you see this model when we get there, it's not good at all, basically because of the weight initialization that they're using. I don't know why they do that. Maybe as a counter example. So you would want your loss to be as close to 0 as possible, and your accuracy to be as close to 100% as possible, right? And that's you see here we're jumping ahead, but the loader testing data is what you use the testing data to do the model evaluation, and then print out the loss and the accuracy. Of course, the closest you have to 100% accuracy, the better it is, right? And there's all sorts, that's the simplest answer, right? There's all sorts of like actual statistical models with precision and recall and number of false positives and test false negatives and all that stuff that you can do. And I'm not showing it here, but you can see it in the machine learning literature a lot. Is this ROC curve? It sounds like a fancy, confusing name or whatever, but just to tell you, it's essentially false positives and false negatives, which I'm sure you all are very familiar from classes or statistics and stuff like that. So this ROC curves, yes, it says here precision recall curves, is a standard thing that if you wanted to go a little bit more than the loss that we showed here, and the loss that we showed out here, if you want to go a little more statistical modeling, the learning of your model, that's what you would use, which is pretty standard. You can read on it, and there's codes out there which you can use very easily to make that stuff. Yeah, so that's a pretty standard thing they're using, and if the curve has a certain shape, it means that your model is trained well. So that's the approach that you would take. Okay, any other questions? Okay, Afsana, go ahead.
Kind of a similar questions to Miriam, but I was wondering, how do you kind of choose, like you said, you choose like 80% of your data to be training and 10% validation or testing. Is there like a statistical way to choose them, or is it kind of like arbitrary and you kind of just see what the predicted results are and you edit it? Like, how do you kind of choose how much of your data to, because it makes sense for the training data to be the most, but how do you choose it for the rest?
The standard is, I mean, some people, they do 70, 15, 15. Others can do like 80, 5, 10, and 5. So it's kind of, like you said, of course, always, and we all understand that the testing, the training is going to be the biggest chunk. But then there's not a hard rule on how it's going to be the other chunks, right? And I would say you know, the most common thing would be the 80, 10, 10. I mean, you could do 70, 15, 15. But that's pretty much what it would be always. And you can also search the web for the splits to do, but you never see something like 50 training, 25 validation, 25 testing, because the problem there is that usually the data is very difficult to come by, in a sense. Even if you have 1 million images, yeah, that's a lot of data. But then if you had 1 million images, you would want to, because we always want to get the best we can, right? So if you had 1 million images, you would try to build a very, very complicated neural network. And because the network would be very complicated, then this number of images still would be like little data for that network. So you want to use your data, you always want to treat it as very valuable and difficult to come by. So essentially, if you only using 50% of your data as training, and the other ones is validation testing, essentially you're wasting 50% of your data set. And the research has shown also that even if you use larger validation, 25% of you use 50% training, 25% validation, it's really not going to make much difference in like catching the overfitting of your model. So with 10% validation, you're fine to catch the overfitting of your model, right? Just don't use like 1% for validation and 1% for the testing, right? Because then you're not going to catch the overfitting, and you're not going to catch the errors in the testing, because that 1%, very few data points that you chose for testing, I might all fit perfect, and then you think like, oh, my model is very good, and I'm ready to unleash it, but it just happened that the ones you picked in the 1%, there's the ones that work perfectly, and then if you chose some other ones, or if you throw like real unknown data, your model is going to make wrong predictions, right? So you always want to keep like a decent percentage, but after some point, it doesn't make a difference to get a huge percentage for validation or testing. And of course, you have to think about randomization too, because at 80%, what you would do is like pick it up through a random distribution from the whole data set, right? So if your data set is arranged like 1, 2, 3, up to 56,944, the way, and I don't know, actually, we have to look at the code. If we do it here, we have to think about that. But you wouldn't pick up, I think we actually don't do it here, so that may be part what contributes to the model being given like not so good training. So you wouldn't pick it up as 80% from 1 to whatever it is, 44,900 being the 80%. You would just use a way to randomize and pick up that 80% chunk randomly from your whole data set, and then the same thing for the remaining 10% for the testing and for the validation, and 10% for the testing. Right, so always randomize it to pick it from throughout your data set, which is what we don't do here, and that's good that we discussed. But let me answer the masking here really quickly. So the way it works here is essentially think about laying out. We explained that the last time, laying out your nodes in a line 56,944, and then putting sort of an array of true falses on top of them, and just use it as a mask to mask what's the training data, what's the validation data, and what's the testing data, right? And then I'm not going to explain the code here. Please see the early lecture for that. But you can see from the output here, so that you see here I'm printing the first the training mask. I'm printing from 0 to 5 ... 44,900 to 44,910, right? So you see the mask here starts from 0, yeah, and see we don't do it randomized here, definitely not. We don't do it randomized, so we start from 0 through up to so this is the 44,910. So I guess up to 44,906. So 0 to 44,906 is all truths, and that's the first 80%. 44,906 out of 56,944. That's the 80%. I think it works to about 80%. You can double check it. Of the first chunk that we get as training data, right? And then the second chunk from 44,900 to 51,410, which I print here. You see, so this is the validation, which you know, the validation doesn't overlap with the training, right? So up to here is training. So in the second mask, we put everything from 0 to 44. I believe 906 will be here, which was the previous one was the training. Now in the validation mask, whatever was a training from 0 to 44,906, we set it as false, and then we set as true the 10% of the validation. So that's going to go from 44,906. So I'm printing like a range here, which has a 906, and of course the first part of the range is going to be false because it corresponds to the training data. And then 44,907 up to somewhere in here, it stays true. So that's there's the so the first mask is like a big chunk of true for the training, and then the rest false, right? So the second mask for the validation data is the big chunk which was true for the training in the previous training mask. Now it's going to be false, and there's a chunk in the middle which is true, which is the validation, and a chunk in the end which is false, and that's what you see here as a printed, which is what's going to come next when we go to the testing mask, where the first big chunk 44,906, which was true for the training, that's still going to be false, and then the middle chunk, which was true before for the validation, that's not going to be false, and we're just going to have a little chunk in the end, which is going to be true, as you see here, and that's going to be the one which is for the testing, right? So again, if we were to draw it, there's 3 masks: training, validation, and testing. And the first mask, and remember those masks, they just go with true, false values over the nodes, the 56,944 nodes, which are arranged in the line, and then they just mask the nodes as true or false. Just basically mask them as for the training chunk, the validation chunk, and the testing chunk, right? So the first mask, it has that big chunk of 80% of the data as true. That's my testing, and everything else is false. Then the second mask has that big chunk as false, because that's the second mask is validation mask. Then it has a chunk of truths in the middle, 10% of the data being validation data, and a chunk of falses in the end, that being the testing data. And then in the final mask, you have false for that big chunk in the beginning of training data, another false for that little chunk of the validation data you had in the middle, and the true in the end, that chunk being true for the testing data, right? And try to visualize that in a line how it is. But essentially, that's masks which go over the data and mask it to get it the 80% training, the 10% validation, and the 10% tested, right? And as obviously seen, it's not randomized. And as we mentioned, that might be contributing to the problem why this model is not trained very well. And let me, so is there any questions regarding that? It's just like, you know, one of these sort of nitty-gritty things you need to understand, you know, how the model is structured. Let me know if you have questions in regards to that. And I'm going to do the next 2 cells, and then we could take a break. I don't remember if we actually covered those in the last time, but it should be it's pretty straightforward to cover them now. Okay, so there's no questions. So there's this code here, which basically what he does, it just initializes the weights, and the way it's initializing the weights is as following. Let me run that thing too. It just counts how much is the percentage of truths and false in each mask, and just uses that percentages as weights, right? Which I think that's where the model also it's not very well. So, you know, if we we're doing very advanced coding here, you know, I would ask you to go find a different initialization schemes for the weights, or actually I might put it as a code that I pre-write, and I just ask you to run it and tell me what happens. So we might do that as a learning example. But what he does is basically, you know, so the first big chunk of the truths, right? What's their portion? We have there's 44,000 of them divided by 56,944. It's going to give you a small number, right? So let me see. So it just divides how many is the non-zeros. Let's type mask to weights, or is that 1 divided? I think what if I have it correctly is basically divided number one divided by the non-zeros, right? And because in the first mask is 44,906 non-zero, so I think if you divide 1, you divide 1 by 44,906, if I'm correct, it's going to give you that very small number. So that's the first weights that is set fixed throughout, which is not good. And then for the second mask, which is that 10%, which is going to be which is the chunk in the middle, which you see here, right? The zeros with the fourth in the beginning. That's the validation chunk in the middle. So I think he divides 1 by 44,9. No, it's not 44,906. That 10% chunk is going to be like how much? If we look at the numbers here, it would be like about 6,500, 7,000, in the number. So if it divides 1 by 6,700, I guess you get that number. And then he sets that as weight. And the same thing for the last chunk, which is going to be how much? I mean, this goes to 56,944. So let's say that's going to be about 5,000. So 1 divided by 5,000 is going to give that number. Let's try if it's 1 divided. Yeah, it's about that number, right? I mean, it's not exactly 5,000. It's ballpark is 5,000. Yeah, so it divides 1 by 5,000, which is the last chunk of truths for the testing, and it gives you that 0.002, right? 1 by 5,000 is, I mean, it's 0.0018, right? Which you see here, because it's probably a little over 5,000, maybe 5,500 or something. And that's what it sets as the weights on the last part. So yeah, so you go the weights, like you try, it makes them fixed throughout, where if you use like if you read the documentation, for example, how does TensorFlow, what's the internal mechanism to initialize the weights, it uses a Gaussian distribution or other distribution you can specify, like some decent statistical distribution. Here there's no distribution, there's like all of them the same throughout, and some of the weights they're initialized by that like very small number, and then because that's 1 divided by the 44,906, which is the amount of training samples, and then 2 bigger numbers also fixed throughout. So very bad weight. So it's like on purpose kind of making a counter example of how not to initialize the weights and how we can end up in a bad train model, right? So that's what it does here. But it's good. Counter examples are good for learning and for science. Yeah, so let's stop it here and then come back to see the actual training of the model and explain the rest of the concepts. Is there really quickly any questions regarding that stuff? I mean, those ones with the mask, you can see in detail the previous lectures. We explain again today, and then with the weights, we don't really need to go crazy about it. We said like what's going on. So we might also see if we can use our own modification to that to make the weight initialization better. So do you guys have any questions on those? You can think during the little break and then ask me afterwards. So let's take a break until 11:45 and be back to continue that. And think of any questions you might have. Please let me know, or the voice or anything like that. Okay, confirmation in the chat. That's great. So now let's talk about building the model, and we're talking about the code. So there's 3 things there, which it's unrelated with the 3 things that we mentioned before, with like training the model. This is 3 things how you write out the model in TensorFlow. So it's kind of a mnemonic, 3 and 3 to remember. So it's the model definition, the model compilation, and the model fitting, right? So I put here throughout the code the links. So here's if you want to read about the you see it says Keras model, because as we said, the TensorFlow is built on Keras. So basically that's the library documentation for developers, and then you can see all the I mean, there's obviously a lot of methods. It does many things, but you can see all the methods here. The ones we'll be using is the feed, compile, and define the model, which is not actually a built-in method. It's how you write out the model. So you'll see there's 2 different ways. I mean, I don't expect you, unless you really want to go into the development side of things, to really read that in detail. But really quickly, you see there's 2 ways to define the model, as a sequential and a functional model, and we'll discuss about those really quickly here. But going back to our code, so for the model definition, it's pretty simple here, because we said we use the graph convolutional neural network, which is one of the pre-built models, which has all the layers built in one model. So essentially, the first phase of the model definition here, which under normal circumstances should be define the layers manually, which is what we're doing here as an alternative way, which you run next. That's something I added in addition to that default code that we're using here and got from Spectral. So normally in the model definition, you would add the layers, which you see as graph convolutional network, but in the regular convolutional neural network should be convolutional network, then a pooling, then you can have another pair of convolution and pooling, as we've seen, but here, you know, I just have a single pair, convolution and pooling, and then you just do the dropout and the dense, right? So that's how you would define your model. But here, essentially, it's number one, model definition. We just get it ready from Spectral. So we just assign the model to a variable, basically, instead of having to define it, right? Now the second phase is compiling your model, and then also before I go there, here's another link I have. I'm just pointing the link. Some of them might have opened already. So this is an example, like for a traditional convolutional neural network, how you know, I mean, it gets the cipher data set, which is like very fairly low resolution images, but they work just fine because, you know, the neural networks just look for patterns in the images, right? So you know, those are the images and those are the labels, and then you know, just to connect that to our codes, if you had, so you see like how many different labels you have. Frog, track, track again, so 2 labels. Deer, automobile, automobile again. I'm not counting, so I'm counting like frog, track, track again, deer, count another label, automobile, another one, automobile again. I'm not counting. Bird, I'm counting 5, horse 6, and so on and so forth. I can keep counting, so I see how many is in my set, and you know, might be 121, like we said before, it might be 80. So that's the same idea here, like how you're going to one hot encode it, right? Yeah, so it shows you here the data set, but what you want to see is like how you define the model, right? So that's he initiates a sequential model, and then that's the model definition here, which is adding layers. And you see the pairs, convolution, pooling, right? So that's the first phase, which for the beginning, I'm just using basically the pre-built model from Keras, which has all those things defined inside. If I was to define, I would do it like that. Now you'll see a difference between how this is written out and how this is written out, and obviously, so see, it also adds the final layers. And if you read that tutorial, you see like it has convolution, pooling, and then at the end always there's a flattening and there's a dense, independently of how many pairs of convolution pooling you have. Always in the end, it's going to be a flattened one and a dense one. But you'll see here it's much more cleaner, and the reason for that, and that's what you would want to use if you use those traditional image classification or text classification, is the sequential model definition. The Spectral still doesn't have that implemented, so you can only do it with the functional model definition, which is essentially just a little more complicated in defining a class for your model, and you know, just getting the output from one layer. See, that's the inputs. The one layer generates an output, and just giving that output as an input to the next layer, which is also what we've seen conceptually in our theory, right? You have the layers stacked, and the output from one layer goes as input to the next one, does the calculations in the neurons. The output of those calculations, the neurons, goes as input to the next layer of of neurons, right? That's the same conceptual idea that we've seen before. It's just different coding style, the functional, which is the only one that Spectral implements, versus the sequential, but that is in TensorFlow in that example. But TensorFlow actually allows you to do both the sequential and the functional, but you're always going to use the sequential because it's simpler in the code and syntax. The Spectral here, they only have implemented the functional option, and that's what we're using. But we can leave that manual model definition from now. And as I said, let's get the one that's ready from the Spectral. So I assign that in our model. So that's step number 1, definition of the model. Step number 2, compilation of the model. So what does compilation of the model means? It's kind of code. I mean, I'm sure many of you or some of you, if you use like compiled languages like C or Java or whatever, when you do the compilation step, if you have, that's the compilation errors. If you have some bugs, it prints out and complains, right? Same idea here. If your model is not defined properly, it's going to print out the errors and you have to correct that. But also in the compilation, you build in the loss functions and the optimizer functions, right? And that's what you see it here, the loss function, which we imported before, and we specify it here, and the optimizer functions, which we said is for the gradient descent to calculate the weight adjustment, right? So model compile, if you go read the model, which I've linked already, I've linked up here, and you need to go read those. So model compile method, you'll see the parameters of the compile method, which is the optimizer. He uses RMS prop. We use the Adam, and we specify a learning rate. I'll tell you a little bit what the learning rate is. You could actually, we could do that as an exercise in the homework. Go change the optimizers and see how the metrics of the training the model change. And loss, I guess by default, you don't need to specify one, but in that case, you know, how would you assess your model? But I guess it gives you that very basic option. So, and there's other parameters too, but basically here we just call the compile method in the second step of after we define our model, we'll compile it and specify those 2 parameters that you see here, right? Now, as I said, here in the documentation, it gives the RMS prop as an example. Here we use the Adam optimizer, and we have a learning rate. And does somebody know what the learning rate is? And could try it or try to make a guess and tell us what you think. Any ideas? So the learning rate basically is how much to adjust the weights on each cycle, right? So you can have a big learning rate, and that means large weight adjustments, or you can have a small one. You don't want to go to those extremes because large adjustments, it might means that you know, it makes big jumps on the weight changes, and you might miss the optimal training of your model, or might go totally wrong the training. And you don't want to have very small training rate. So it means make very small changes in the weights, because it will keep training forever, basically. So when I keep a balance between the two, and you know, you might be thinking, what's the right thing to do? It's more like experimentation, right? Or again, like we were saying with the training and testing data and validation data splits before, that you use the 80-10-10. Here, learning rate, you'll see like people use the 0.001. So essentially, it makes like 1% change on each like cycle. Mariam, you have a question?
Oh, I think you just answered it. I just wanted to confirm if it changes by 1% each cycle, or if it goes by more than that.
Yeah, so 1% on each cycle. Yeah.
Thank you.
And there's of course, you know, how the learning rate plays with the optimizer is a big is a whole research area, and you have of course to read those papers that you see, like references there, and you see what's the right optimizer for your data. I mean, I don't even remember exactly. We could read the documentation what the Adam does, but let's assume that since they use that here, that works best with the graph data, right? But that would be another whole like open sort of thing to research, to look into. And then that last one, which is also, I believe, well, this is bundled. This is the k-args as additional parameters which are not specified here. That's where this falls under. And the k-args is a Python idiom, right? And this is to keep the weighted metrics to save during the model. And this is, what is the ACC? Accuracy. So that's the accuracy. So as you train the model, just save the accuracy to print in the end. All right. And you can save all other sorts of stuff. Which actually we don't need here because we, in addition to their spectral code, I added the tensor board, as you'll see further down. So we write that through tensor board callbacks, and we just pull in the metrics as the model trains. So even if you didn't put that, doesn't matter. This actually, if you see further down, is for printing out that stuff. That's why it keeps the accuracy during the train of the model. But we actually, if you compare to the original Spectre code, I added this tensor board callback, which I pulls it and puts it in the tensor board, which you see is a very nice way to visualize the metrics for the training instead of just printing dry numbers for the accuracy and the loss in the end. The tensor board, like, it gives you very fine grained graphs, and those graphs, as you'll see, if you have, like, in ours, it was going to stop in like 10 cycles, but if you have models which run for thousands of epochs, complex models, in the tensor board, you can summarize all this data, zoom in, zoom out, which you wouldn't be able to do by just printing out like just dry accuracy numbers. Okay, so we define our model, we compiled our model, and also the tensor board, we need to specify it in advance. And let me tell you a little bit. You see it, what it is, but here I have the link to the website, and there's also suggest to go read it. So this is basically visualizations. This is the actual the training. You can see the actual model as a graph, and this is a dashboard basically to see the metrics for the train of your model. And in our model, we're just going to get like two simple graphs, which will show us like how bad our model is. But you know, that's hopefully not the case. Usually, and it's used when you train like really complex models, so you can really get fine-grained visualization statistics, how your model train is doing, and you can use that as a feedback to sort of spot like where you need to fix things, rather whether you have some erroneous data, or you need to adjust your data splits or your learning rates and those kind of things. So, you know, this is a whole lecture on itself, right? Which we're not obviously not going to do, but you can just use it as a tool, and of course, go like read it in more detail. And if you ever do this kind of work, get to know it and use it, you know, to your advantage in building like good machine learning models, right? So what we do here is we load it in advance. This one is what they call in Jupyter notebooks, because the collaboratory is a Jupyter Notebook is a reminder. They got the Jupyter notebook open source code and integrated in Google, right? So this is interactive Python coding notebooks, right? You could use that if you install everything locally, right? We use it in a Google Colab. So this is what they call the magics to load external graphic libraries. And here we import like datetime, just Python function to print out the date and time, and basically create a directory. I mean, you could just name it with a fixed name, but here's a fancy name to create a. Basically, this is a directory which saves out the metrics, writes out in files, the training metrics, accuracy and weights and everything of the model during the training, so that can be read from the directory from the tensor board and visualized, right? And I guess it's just using a fancy name for the directory, which is good because you put the datetime. If you kept training your model with new parameters day after day, it would just save directories with different names based on the date and time. So you can always go back and load the data on TensorFlow from a previous training run and visualize it and see what's the difference, improvements, or getting worse between your different training runs with different parameters, right? And this is a callback. Callback, essentially what it means, just use it as it is. We don't need to worry too much about it. It means like calling the model to send data back as it trains, so I can save it in a directory. That's all it is. And then you just define it as a callback, and then you're gonna throw that into the model during the training process, so it can pull out the data and save them in these directories. And this one, it means like I believe in write the data at the end of each epoch, right? So that's, I think, what the frequency is. But again, we don't need to worry too much about that. So again, we defined our model, right? We compiled it. There was no errors during the compilation. We set the loss and the optimizer, which we discussed about that. So step one, define it. We'll just call it as it is. Instead of defining manual that it's here, I'm going to skip that cell for now. We compiled it, and now the third step to actually fit the model, right? So if you and before the fitting, we load out the tensor board. We define the callback, so we can use the tensor board callback to pull the training data from the model as it gets in fit. And fit means like fit means train, right? They could have used the method training in the TensorFlow, but I guess they chose fit. Fit means fit the model to the data, or train the model to the data, right? And you can see that, like, if you go to the model here, the methods is the fitting, and you can see what parameters it has. And we'll go over the parameters that we use. But before I explain the last part, the model fitting, do you have any questions regarding these concepts we just discussed? No questions? Okay, so then we can go ahead. So we see then a little bit more of Spectral here. So Spectral has this what we call the data loaders, and again, the reason for that is because we're basically trying to fit square pegs in a round hole, meaning that remember the whole graph, the graphs being like balls and sticks kind of thing, which then you try to fit on a grid. The graphs obviously, like as balls and sticks, is kind of a randomized structure, and the grid you're trying to fit them is the tensor, right? The multi-dimensional matrix, which is like a fixed thing, like as a grid. So that's what the part of the grid functionality that Spectral provides, is to fit the graphs in the tensor that can be used in the TensorFlow framework, right? And a lot of this functionality happens by the loaders, and you can go on Spectral and read about the loaders. So for us, since we have a single graph, I'm going to be using the single loader, right? So essentially, it loads like the whole data set in a single pass. And when I say the whole data set, I mean the whole chunk of data. It might be the training chunk of data and the validation chunk of data, right? And remember, the way you did that is you masked part of the data, a big chunk as training, and a smaller chunk in the middle as validation, and another small chunk in the end with the true falses, right, as the testing, right? So here we use the single loader. So we're going to get from our data set with the masks and the weights, which is going to get the chunk in a loader, single loader. We don't need to worry about much how this works for our training chunk, and then for our validation chunk, right? And again, this is our whole data set, and this is the masks that we prepared before. You can look further up. So we have the training data and the validation data. Like essentially, if you read the documentation there, you see like for the model.fit, the train of the model, it could be it is the training data that you give, right? So that's the essentially the first is the X, right? So we give the training data, the X, the input data, if you want to make it correspond between the two. And then there's some more parameters that we use, the steps per epoch, and then what's the validation data, right? And that's right here as well, right? So that's our what is it? The steps per epoch by default is none. And then whereas there's the validation data by default is none, but obviously you always want to use validation data, right? So the X, which is the input data, we just use the loader TR for the training data, and we call the load method. Remember, the loader again is essentially an object from Spectral, which converts the graph to tensors when you call that load method. And we got that object from basically that's a variable which gets assigned the object, the single loader, which is for the it has the chunk for the training data with the mask that we mentioned before, and there's another single loader which is assigned to this variable, which has the part of the data set with the mask for the validation data, right? And then that's what we do here. What you see in the original TensorFlow documentation, that's our input data, X. I guess you can run a model without input data. That's why its default does none. Doesn't make sense. So our input data, which is always the first parameter, we call the load method from the single loader, which was the object which was assigned to this variable up here. And then that's the cascading, like getting our data set, applying that mask, and getting that first chunk of the data as training data, and that's right here. And also we give validation data, same idea. We get the loader, which has the mask for the that middle chunk is true, which is going to be our validation data, and we load that as well. And then these parameters, you can actually we can actually print it if we want. Let me see if that's going to work. May will work because I haven't defined it yet. Yeah, we haven't defined it, so it doesn't work. So you see this one, steps per epoch, is just going to be well, why don't we I don't know, do the following thing. Copy that code. So see how many steps we'll do per epoch, which is essentially the batch. Yeah, let's print it here. So we see it. And then how many epochs, that was defined all the way up in the beginning, 200 epochs. And then the learning rate, I mean, that was in the compiling of the model. And then finally, we have the callbacks. So we mentioned before, that was already in the code as I got it from the spectral. The early stopping, which we explained, you give one metric when called patients. So when your model reaches a certain threshold of training, instead of having to run through all the 200 epochs, it just stops there and it saves you computational time and avoids the overfitting as well. And then restore best weights. True, that means like, you know, if you got past on the threshold, to just, and you have adjusted the weights, to just dial the clock back and go to the exactly previous cycle, which had the optimal weights before you crossed that threshold of overfitting or overtraining or whatever, right? That's all there is to it. I mean, this stuff you have to obviously really dive in the documentation to really understand it, but I'm just giving you the definitions here. And that's the one we added, the TensorBoard callbacks. In this is an array, right, which you add as many callbacks as you want, and essentially the callbacks is to just save data, like because remember the model as it gets trained, you know, the weights change during the process, and other data, other model parameters change too, but essentially here we're interested mostly on the weights and the errors. So the callbacks, what they do is like just to pull information out as the model gets trained, because otherwise, you know, would we get trained in cycles, and each cycle the weights change, on each cycle, and unless you pull it out from the model to save it, you're just going to get the final output, right? So that's what this does here. In other words, kind of pulls the data out to keep track of the history of the training of your model, right? And then having that, now we can go ahead and run the final step of fitting the model. So you see it start running the epochs, and it's not going to go all the way to 200. You see it stopped at 16, because what happened is at about 16 we crossed that threshold of patients, and which means like it was trained good enough, and it just based on that callback, it's just stopped the training, right? And of course you could experiment, and that's something else. We could try the homework and just go to change the threshold and see how it changes the training, how many cycles. So if you put it less, or if you put it more, will the cycles go more or less, right? And then if we go to the files, you see the directory logs created here, which is what the directory defined it there with the TensorBoard. And here it just saves all the metrics for the during the training, what weights get set there in every cycle of the training and during the validation. And then from that directory is where TensorBoard is going to read and give us the nice graphs with the metrics, right? But if we didn't have the TensorBoard as it was originally there in the code from the spectral, from where I got this code, basically what you would do is do the model evaluation in the end. So now here's another loader for the testing data. Loader T means loader for testing data, as loader TR and loader VA meant loader for training and loader for validation before. Again, the same thing, our single loader, our mask weights training, which if you go up in the code, you'll see is the last chunk of the truths masking the data, that last part being the testing data. So essentially now model evaluate, right? Again, if you go on the model. On the TensorFlow, you'll see the evaluate, and then it tells you what the parameters are, and then essentially returns the loss value in the metrics for the model and test mode, meaning that after you train the model, you throw in the testing data and get the loss and see how well your model performed. And here is the methods you can have. We just basically we don't use any methods. We just give it the data and say the steps per epoch, which is actually not really needed because you know, basically do everything. We don't do batches here. If you print that, let's see, actually, I print up here. So you see that one here. Where is it? This one. Let me see. No, this here, I believe it's from that print command. So essentially, it says one batch. That's what steps per epoch means. So we give the whole data in one batch because it's so small, right? If you said 10 steps per epoch, it would mean like you would split your data in 10 batches and give them like in batches, or the whole thing that we explained before, not to run out of memory and all that stuff, right? But here it doesn't apply because it's a small data set for machine learning standards. So even if you didn't put that, it wouldn't really make a difference. So essentially, we just give our testing data set, and we call model evaluate, and it's going to return, and I guess, what is that? It's an array or something, or is it a hash or whatever, where it has the metrics, and we just print out the test loss and the loss with the testing data and the accuracy with the testing data. And as you'll see, I mean, this is like just raw numbers from the loss function. So depending on the loss function, this number might be up, might be down, it doesn't really matter. But you know, you can see it right away here that our accuracy is basically 2.3%. So not good good training at all, right? And that's what I mentioned before. But anyway, this is a good sort of counterexample in your exercise. In the homework, as I see it shaping to write it now, it's going to be like try different number of patients, so we can write it run for more epochs, and also remove that part where we set up those fixed weights and let the TensorFlow set up the weights, and then see if that improves the model. So that would be a fun thing to try, and be excited to see if we can make a better trained model, right? But besides that, then we can, let me finish the tensor board as well. So since we're talking about the crappy errors, so I can show you that, and then you know, we'll open up for questions and then wrap up. So then essentially we don't just, instead of seeing plain numbers, which is fine for here, but we said like for more complex models, the tensor board can be great to visualize your training runs. So then basically, again, the Jupyter Notebook magics to display graphics inside the Jupyter Notebook. So we just call the graphical dashboard of TensorBoard and say where's the log directory, which we specified before, where I was saving the weights and the training metrics during the cycles for training. So specify that, and let's go ahead and launch the TensorBoard. It might take a few seconds to do that, to appear the graphics, because this one runs remotely. So what happened now? Interesting. I mean, we specified that before, right? I don't know why that happened. We have a tensor call, but that's interesting. Okay, retrain our model and rerun it. That's interesting. I don't know why this is happening, because I tried yesterday, it was working. Let's try one last thing. You guys think about like questions you might have. Let me delete that folder. Okay. Well, I can write a different one. So is there any questions regarding what we discussed that file? Actually, I want to recompile the model. And rerun it. And I'm putting an alternate directory for the tensor board. So what is the logs directory? Okay, so maybe that's the problem. Let's see, so it's under okay, so maybe it's under, let me see, before I train it. So maybe it's under slash. Okay, so maybe that's what's wrong here. Let's see now. Would that work? That might work. Takes a little time to bring the graphics because it's more okay. So still not working. All right, let's rerun it. Logs alt fit. So I'm going to create a different directory and then rerun my training. Yeah, because I tried it yesterday, it was working. Okay, so all the epochs are here, and then you see the logs out is here. And let me make sure copy path. All right, so I could, I rerun it with a different directory, as you've seen. All right, let's try it again. Content. I see now, forget like. Okay, it seems it's not. Okay. All right, so I guess it was working. So I don't know. Was it working with the data before? Let me try the other data again. I guess the problem was like we didn't specify the directory right correctly. So you need to put slash content logs. Okay, we corrected it now. Yeah, or maybe it needs a little wiggling back and forth or something like that. So I don't know, one of the misters that happens sometimes. But anyway, so and you see here, I guess what we're showing is like how you can change the directories if you run like I mean, here I changed the name, I hard coded, but the better way would be to like specify there with the date that you're running, and then just change the dates, right? That's more intuitive to keep track like of your computation experiments, right? In subsequent days, you modify those parameters, you keep a lab notebook, and then go load on TensorBoard. They run for that date and see like what has changed or what has been improved and stuff. But again, you can read the TensorBoard, the whole documentation here. But for us, what we're going to show really quickly, the graph we don't need. I'll show you then what's a graph is. What was this dry printout of the test accuracy, which is the final, without seeing what's going on inside. If you want to see what's going on inside during the training, right? Accuracy and loss during the iteration. So you'll see here, as we have the iterations of our model, basically the accuracy goes up, which is what you expect, and then you would expect the loss to be not like that. You'd expect the loss to be a line just going down and then just reaching asymptotically towards zero or a minimum like 0.1 or something, right, to have a minimal loss. But you can see here something is really messed up with the model, because you see the loss like going down, but it's not like really going down. It's just going down by really percentage points. It just hovering over at 171 and then just shooting up again. So you would never want to do that. I mean, it's and you see there per steps, right? And actually it doesn't really change much, but this is not the right graph to see. You would want to see the loss going down and, you know, staying minimum towards the minimum asymptotically, right? So that shows you like what you don't need to see. And let me show you really quickly, then we'll go to the question. So the graphs, this is going to look a little more complicated because you know, the spectral makes its own model inside. I don't know why the graph doesn't appear here. Maybe something on how it loads and stuff, but it essentially would show you like it's a graph, not as in graph like histogram or whatever, but it's a graph that shows you like how your layers are structured, right? Kind of like the graphs that we had in the homework where we showed like how the hidden layers are. That's what this graph visualizes. So, you know, essentially it's been used when you build like complicated models to be showing you you know, how your model is structured, right? Obviously, in a simple model, you don't need that. You can keep that in your head or just figure it out from the code. But when you have like very complex models, that's where these graphs, which shows how the layers are structured, can be used. And many more things you can get from TensorBoard. And yeah, let's go to the question that Guy, you have.
Thank you. Before those graphs were going up sort of parabolically, and it was getting worse. Do we know what to attribute that to? Is that overfitting or is that some other?
I think my main culprit is that thing that he's doing with the weight initializations. So I can put it as an exercise in the homework. That whole thing, where was it now again? Up here. That whole thing to go out and not use like these very totally off weights and totally fixed, and where it's see where it's specified here. Maybe we could try it really quickly. Well, I'll leave it for the homework. So where's the weights? So here, if you could just remove that and see if it works. Let's see. Let's remove it now. Will it work or will it error out? It actually works. So let's remove the weights specification. I mean, we have the code above, but we don't use it. So we're assuming that the TensorFlow is going to take care of initializing randomly the weights on its own, and so rerun the model. And I guess it didn't really make a difference. So the accuracy is still bad. And let's make sure. Sorry, I need to let's make sure we have again the TensorBoard correctly. So I'm gonna do an alt 2. Okay, so I specify the directive in TensorBoard, and then that's alt 2 is built in there in the callback, which has been given in the model right here, and you can see like created that new directory. We retrained it, and then you're not going to see much difference here. So let's get this directory, copy path, and let's put it in here. And let's see now if we get different graphs. Let's see. Let's run our TensorBoard. So that's my main culprit. If that doesn't improve, it seems it doesn't. It might be that I don't know, maybe the whole data is messed up. Because remember this graph, Sage, it was actually made as a big graph to benchmark graph algorithms. So it might not be the ideal one for the training. Okay, so let's see, loss versus iterations. Yeah, now it's even worse actually, because the loss, it just goes straight up. So, and the accuracy, you see here, like the accuracy actually goes up and then it drops down again, and it goes up again. And I guess we did like, did we do like 40, how does it show 47 epochs? That might be weird. No, actually the epochs are here, so I don't know what the iterations mean. Anyway, that's going to be investigated. But yeah, intuitively you understand like what it means, that how the loss should be going down and the accuracy should be going up, right? And here it's kind of going up, but then it's going down again. So that doesn't look good. And you can, let's see if we can find it now. Let's see, accuracy, plots, best or something, right? So we could put this as an exercise, how they should look ideally, right? So yeah, so you see here the training validation, the loss keeps going down. So we'll put that as an exercise, but you understand intuitively like how it should look. Did that answer your question?
Yeah, a little bit. Thank you.
Okay. Yeah,
But
it's a lot of concepts too. Yeah.
I have another question.
Yeah, go ahead.
I think you may have mentioned this before, but I'm sorry I missed it. The difference between the load_ext and import.
Where is that?
In the code for the tensor board, where you do load_ext.
So this one, right?
A little further up, but yeah. No, that one, but yeah.
Yeah, so this is part of the Jupyter notebook to load an external graphics inside this notebook. So yeah, so that's just load an external graphics library. So you could look like Jupyter notebook, Magix, load graphics. So there's a whole documentation.
Okay.
Yeah, so you could read it from there, right?
Great, thanks.
Yeah. So because the Google Colab is Jupyter notebook. Okay. Any other questions? So Mariam, go ahead.
I had a question. It's not pertaining to the material covered. It's actually pertaining to the machine learning class in the fall. That was typically scheduled for the fall. I just wanted to, I had like a quick question about that. I'm not sure if you would prefer that to be like an email or a discussion board post.
No, go ahead.
Yeah, so I'm trying to register for the undergraduate section of it, and it's not popping up on the registration.
It's not available yet, but it should be like May 10th, May 15th or something.
No, like
you only see the graduate part, or what do you see?
I'm an undergraduate student, so like the course schedules have opened for the fall. In general, we're not allowed to enroll yet or for registration, but we're allowed to see what classes are available. And I was trying to see, what section machine learning is available for, and it's saying it's not offered for the fall.
I'm sorry, this doesn't seem relevant. So is class over or?
Yeah, for those, if you guys don't have any questions, you guys can go ahead and we're done for today. And as we said, asynchronous next time, homework will be posted and one final. And I'll also say all that stuff on the Blackboard. So get back to Miriam's question, and if anybody else has additional questions, you can stay. I'll be here. We can answer them. So we saw the training models for the day, and the last part basically is for exporting that TensorBoard graphics on the public website. But as I realize now, it actually needs some interactive, and I don't know how to press yes here to push it on that website. So I cannot do it, but you can read about it, how it works on the TensorBoard tab. So that's with the class today. We're done, and thank you for attending. And anyone who wants to ask questions, you can stay. So Mariam, can you tell me again? Let me stop actually the recording.
Was attendance taken